Hello and welcome to all the viewers. In present video, we will going to discuss about a structural analysis of Gantry crane part 2 using ANSYS workbench. So the present video is continuation of first part. So if you remember, in first part we discuss about a geometry simplification part. So if you see, this is nothing but our Gantry crane, which consists of a hook, and this hook will going to carry the respective load. So now in first pass we discuss how to simplify the geometry, mid-surface extraction, then few geometry editing as well as extension operations, as well as we discuss how to create a weld and then how to check the surface normals, as well as how to define the connectivity in SpaceClaim. Now in second part we will going to discuss about the actual mechanical part. So here very first we will discuss about how to read the geometry in mechanical, and then how to perform meshing, loading, how to apply loads and boundary condition. Then once your solution is performed, then how to extract the results such as your stress as well as deformation. In addition to that, we will also check how to perform the reaction validation. Okay. Now let's discuss about the actual problem statement of our present video. So in this, we need to perform the structural analysis of gantry crane for a 500 kg load carrying capacity, and to check the structure of a gantry crane is safe or not for the yield criteria. And the material is structural steel. So basically, this is nothing but your gantry crane, which consists of your steel hook, and here you will find the chain which basically carries the load in horizontal direction. So like here, okay, and the load is like, you can say, 500 kg of load. For that load this crane is designed. So basically you need to think that whether this particular hook will be at central position, at which position your the deformation is higher. So you need to, even you can do the analytical calculation simple, like simply supported beam, and then you can apply the respective load at center or at some overhanging positions like here, okay, and then you can perform the your analytical calculation. So we will going to check the same in FEA. So like, as we know that when this will be at central position, you will find that the maximum deformation will going to occur, and for the same state of application of load we will going to check the stress also. So let's first check this position and then we will check the central positions. Okay, now what we will do, we will go to our workbench and there we will discuss the present simulation. So now we are in our ANSYS workbench project schematic. So if you see that this is what our geometry, and this is what the static structural simulations which I already performed. So now let's begin. I will also repeat the same simulations so that you will also come to know how to perform the simulation. So for that you just need to drag like this, and you can drag over here. Okay, so like if you drag, then it will directly come going to connect this geometry with this geometry, and then you just simply read the model or setup, okay, through this C analysis system. So let's first discuss the SpaceClaim, what we did in first part, and then we will discuss the simulation part. So you can double click, and I had already opened, so let's check this one. So if you see, this is what our the first part where we created the whole geometry. Okay, I will show you further one more time so that you can see, like we have created few welds here. Okay, you can see we also created weld over here, and here this is the bolted connections. Here also you can see the bolted connections, right? So there are different ways to create the connectivity between this. So either you can create a bolted connections, or else you can simply create a bonded contact. So in that case you need to look which is the most feasible case. So like if you are planning to create a bonded contact, then if you want you can even delete these holes, okay, so that there will not be problem for your mesh. So let's move forward now with this, and then you can see like our first, the hook position is over here, which I created the imprint of that respective hook. Here also you can see, right? Then what I did, I also created at the central, so you can see the spin plane over here. So what you just need to do, you just need to copy this. You can do Control C and then you can do a Control V. So once you will do the Control V, you will find that on the top there are two surfaces created, and then you just simply move that to the central position. So like if you move in central position, okay, so you can see like whatever the position of hook, accordingly you can move this and then you can imprint on this respective beam profile. Okay, so let's do further Control Z. So you can do accordingly, so based on your position of the hook. Now this is what all about our geometry creation part, so please do not forget to see the first part. Now let's discuss the second part. So for the second part, so I just open the mechanical, so you can see that the geometry is open in mechanical, and you will see the first, the question mark. Okay, so here you just expand that, so it will show the question mark for the geometries where there is no thickness is assigned. So basically these are the geometries for the weld surface. So you just need to look which are these respective geometries. So let's zoom the part, and you can click over here. Okay, you will find that these are the respective geometry surface. So for that, let's check this respective geometry, go to corresponding bodies in a tree, and here you can see that the 4 mm thickness is assigned. So accordingly you can select these two surfaces, or even let's select the another and right click, go to corresponding bodies in a tree, and over here you can define the thickness of 4 mm. Okay, this is the 4 mm thickness. Now let's check these parts, which are these parts. So if you see here, these are these respective parts. So here you need to check which one will the thickness, how you can assign the thickness. So let's check this member thickness, go to corresponding bodies in a tree. So if you see here, it is 12 mm thickness, and here go to corresponding bodies in a tree, and here it is 4 mm thickness. So what I can do, so let's go with the worst case scenario, and let's assign the 4 mm thickness only. Okay, so select this, go corresponding bodies in a tree, and then assign the your 4 mm thickness. Likewise, you can assign the thickness for the remaining welds if you have created. Now here if you see, in actual we have created the, if you see here, we only created a contact through this weld, but in actual you will find that this body will in contact with this when you have a movement of in Z direction, like when the structure will move like this, or when the topmost force will going to act, it will go down, and then you will also found that the surface to surface contact over here. So right now we will not going to create any contact at that locations. Let's see the results, and then later on we will decide the remaining part. Okay, now once your first part is created, now let's discuss about the material. So now if you see, by default your structural steel material is already available. So if you see here, if you double click, you will come to know that the structural steel is already available by default. If you want to create a new material, you can define, and from here toolbox you can define the respective density, linear elasticity, all these remaining materials. Okay, Now this is what your the engineering data, and let's go to your mechanical part. Okay, so let's check here. Now this is material which is by default assigned to all the components of the gantry crane, and then you will find the connection part. So by default it will create the number of contacts based on the tolerances. So what we can do, we can first delete all these contact, right click, delete, delete, yes. So because we will going to create the manual contacts. So what are these different contacts? So let's check. The first one we will going to assign between these two bodies. So you can either create, right click, insert manual contact, or else you can select, right click, insert manual contact region. Okay, now similarly you can repeat the same for the other position. Let's create over here, select this part, right click, insert manual contact region, and similarly you can repeat the same for this. Let's disable the transparency. If you want, you can hide this. Let's select this, insert manual contact region, and similarly let's repeat for this member, height body, insert manual contact region. Okay, now these are the four contacts which we created because there is no well defined. Now let's create the another contact for the open position. So if you see here, these are the bonded contacts, or you can see the bolted connections will going to come over here. So instead of, let's simplify that using a manual contact region. So for that, let's select the first surface, apply, and then select the another surface, apply. Okay, similarly repeat for the other side face. So insert manual contact region, select the face. Now if you see here, there are two middle faces are missing, so you can select that also, then define here as well as here, apply. So I think we need to further check this respective contact here, and let's select the missing surfaces, this one and this one, apply. Okay, so now you have created all the contacts. Let's define further a few pinball radius so that there will not be any gap. So I will just define 10 mm. Okay, so you can see how it is created. So basically if you click here, it will going to create, so that if suppose the gap is more than 10 mm, then it will not create, it will not going to close the contact. But if gap is within 10 mm, then it will create the contacts, or it will form the contact pair between target and your contact and target surfaces. Okay, so that can be checked easily with the help of here contact tool. So here it will going to display all the whether contact are closed or not. So before that, let's do mesh zoom to fit. So for the mesh part, so you can insert and you can define the sizing. So you can first select all the components if you want to give any particular sizing. So by default it is 23 mm. So let's try with the 23, generate mesh. So basically you just need to check what is the width of this. So let's say now width is 100 mm, and if you want 5 mm across this width, then you can define the thickness of 20 mm. If you want only if you want 10 elements, then you need to define the 10 mm of thickness. So likewise you need to check and you can define the mesh size. Okay, so right now I will not going to focus on a mesh. So you can do, when you will do the simulation at your end, you need to define the proper mesh. So right now we can see with this 23, by default mesh it is a course. Then let's define the size of 10 mm. Okay, and here, so when you will do the simulation, you can remove all these holes, because we are simplifying that with the help of bonded contact. So we replicated bold contact into bonded contact. So in that case, you can even remove these holes, which will create a problem for meshings. Or else you can even define the D feature size, or here you can see the capture curvature. So if you keep it this yes, then it will going to capture the curvature. So let's check with 10 mm size, generate the mesh. Okay. So with the help of 10 mm, it will further do the fine mesh, and accordingly you can check your sizing for each member. So mesh is very important when you have a surface. So you should check the mesh at the weld surfaces, you should check the mesh at the fillet regions, and you need to check whether your curvature is captured or not. So at present I will not going to focus, but when you will do the simulation, so you should focus on all these parameters. So if you see here, you have an option of curvature. So here you can capture the curvature. Even you have an option of proximity. Proximity means like small surfaces. It will also going to capture the small surfaces. So you can keep that option yes, okay, for that. So now if you see, our mesh is completed, okay, with the 10 mm of size. So you can even check for that. I think the mesh is okay. So but when you will do the mesh at your end, I will suggest you can even go further finer, and so you can see here like fillet is not that much capture, so you can even define further finer mesh. Okay, so right now I just want this we should get the result faster, so that is why I kept the moderate mesh size. Okay, so once your mesh is performed, you can click on the contact tool, and here you can just right click and you can generate the initial contact. So you here need to generate the initial contacts. So it will go into display whether the contacts are closed or not. So before simulation, you can easily able to apply your respective loads. So now you can see your initial information is. So if you see here, right click and it will display the far open. So basically red means your contact status is open. So you just right click, go to the selected item in a tree. You can see like that, hide all other bodies. Okay, zoom to fit, and here you can see these contacts are open. So here you need to think like why it is open. So basically when you see here, these the pinball radius is not that much sufficient, so I will keep it 20 mm. So now if you see, we had increased the pinball radius, and let's see what will happen with this, so whether it will going to close or not. So now if you see, our contacts are in close condition, all contacts. Okay, so likewise you need to do, or you need to check the contact status before the simulation. So once your contact tool is done, then our next part is to apply the loading and boundary conditions. So here let's check. So there are a number of ways to apply the your respective loads for this. So the first way is you can directly apply the forces on this. So these forces you can apply on all these four faces. here like this, insert, and you can apply the respective force. So it will going to apply in the form of uniformly distributed load. You can define the like 500 Newton, okay, and here you can define either. So for example, we have 500 kg, so I just giving you the example. We need to apply in negative y directions, so like it should be higher than 500 Newton. So you can according, so you just check the direction, so you can apply like this is the first way. The second way you can apply by using the, here you can define the point mass. So here you can connect all these four faces, okay. Here once you define the four faces, and you can create the point mass at the respective location of your, here suppose you have, let's create the coordinate system, insert coordinate system. You have created coordinate system, let's create this coordinate system. Offset this y, so let's offset y, and here you can define 100 mm. So likewise you can check the respective 200 mm downwise. Suppose your hook CZ position is here, so you can define the point mass using local coordinates 0 0 0. Here you can define your respective weight, okay. This is the second way. And the third way, you can create the remote point. On that remote point you can apply this, but I will suggest let's go with the direct worst case, that is force we will apply on this respective. So for that you should have a load of 500 kg, okay. So how to check that or how to apply that 500 kg, I will going to tell you the simple trick. So let's go to the geometry, home, check the units, and let's change the unit in kg, and let's make it 500 kg, okay. Now you have applied a mass of 500 kg. Let's change the unit in pound, okay. So okay, it is like 11203. So you can copy this and you can apply the force right now, paste, and here you can define this, okay. So now this is value of 500 kg, equivalent to 500 kg. So let's, now we don't want by this way, so I will going to delete. I will going to check this force, and then let's apply the fixed support. So fixed support, or you can apply the displacement. So I will assume that let's apply the fixed support. So we will going to apply on this respective four faces, where you will have the wheel apply, okay, and you can apply even the standard earth gravity. So this is the standard earth gravity, which will going to act always in my negative j direction. So you can change from here and make it 2 minus y, okay. You can check the direction, right. So we had applied the force, you can see on 4, and we had applied the standard earth gravity, okay, and then solve the simulation. So now if you see, our simulation is performed. So while doing these simulations, once you have given run, if you came across some error or rigid body motion, it means that your structure is not completely connected. So in that case, you need to check each and every connections, right. So like here you can go to the display tab, here by connections, and here you just check. Right now you can see it is like, if it is this respective edges are red, it means that you need to define the connections. So now if you see here, even for the weld region also, if you came across some red edges, so now you can see red edges over here because there is no connections, okay. Here there are 3 edges, so that is why it is yellow. You can see here also, okay, there is no red edge except the open surfaces. So in such a cases, so if you came across some error while the simulation, you need to first check all these corrections, and then later on you can check the contact tool. So these are the two ways you can check the connections. If your connections are proper, then you should not come across the error. Okay, so let's check the first total deformation and then equivalent stress. Okay, so the first total deformations, let's click on the total deformation and let's change the unit now, make it mm. Results, let's, so if you see that your maximum deformation is obtained, so let's animate that. You can see how the animation is performed. So when this respect to, this is actually the scaled version. So if you make it true scale, you can see which is 1 mm is very minimum, okay, which is not even visible in the animation. So that is why I'm just increasing the scale, and then you can check the animation. So right now it is easily visible that whatever the load which will going to come, it is proper. Okay, now let's check the your analysis stress. This is the, your stress is having a 25 megapascal, which is quite less compared to the yield. Your yield is 250 megapascal only. Okay, so it means that our structure is safe. So let's check where we apply force. So we applied a force on the center position. So now if you see the position of the force which we applied at the central location, okay, and our hook is at somewhere here, and we already imprinted that also. So let's now change the force and check the effect of deformation. So ideally you should have maximum deformation at when you apply load at the central positions. So let's check, we should have the minimum deformation compared to central location. So I just duplicated that. I will now suppress. I will change these to these 4 positions, 1 2 3 4, apply. Okay, and then solve the simulation. So while simulation is in progress, let's check how to validate the UFA simulation. So for that, let's check the geometry weight. Here you can check the properties, and we have a weight of let's make it in 436 kg or 437. Control C, and let's here how to check the reactions. For that you just need to open the your Excel. So once you will open your geometry Excel, so you just first write down the geometry mass. Okay, geometry mass, then you can write down the load you have applied, and then FEA reaction, control X, right here the total mass you can apply here, total mass. So let's go to the, so if you see here the very first you can check the whatever the geometry mass is there. So you can click on the geometry, and from here you can easily find out the mass. Okay, let's check here. You can write down here, you can write down the 500 kg is a load we have applied plus this. Okay, and then you can check the applied the geometry here, this into 9.8066. okay, so this is in Newton, so our reaction should match with this. So okay, now we can see that our even second, which we applied the force at the second position, simulation is also performed. So let's check the deformation. So make it. So if you see from 1 mm at the central 2.79, so basically 20% deformation is reduced. So we shifted the positions here instead of center positions. Okay. So likewise, the you will come to know the importance of the load, which will going to vary across this vertical platform. So you need to check the worst case scenario, and accordingly you can perform the simulations. And even stress, you can see the stress is quite low. The very minimum stress is there because this structure is quite sufficient rigid for this applied load. Okay. So if you check the thickness, whether we have assigned thickness here, go to the display and on click thick check sunbeam. So once you will click on that, you will come to know the whether we applied the thickness proper or not. You can check the at the junctions, so you can see here. Okay. And make sure that there is no any interference. Let's uncheck. Okay. So this is all about your deformation and stress, which you can easily find out with the help of your respective. Let's check the first the reactions probe, and here you can check the force reactions, and on this you can check the force reaction on fixed support, evaluate the results. Okay. And you will find that this is what the my y-axis reactions. So from here you can check the y-axis reactions, control C. So let's further suppress this and unsuppress this middle position, evaluate, or you can solve that. And meanwhile let's go to the Excel. Here you can put that value. Okay. Now you can check this minus this. So only 7 mm Newton difference is there, so it means that our reactions is completely matching. So if you want to check the percentage error, so max minus minimum divided by max. No. Okay. And here you can easily okay, so only 0.08% difference is there. So it means that the total geometry mass is matching with the FA reaction. So it means that our simulation is proper. Okay. So likewise, you can check the reaction validation. And you can check the total deformations at the central position as well as at different positions. Stress is also very minimum. Let's check the force value. We do have a flexibility of changing the units, so you can easily cross check the units from here. Okay, and you can accordingly check your stresses as well as the reactions in different unit. So that's it, guys. Like we do have a stress which is quite minimum compared to the yield. Yield is 250, and its stress is almost 10 times less. So it means that our structure is acceptable for the yield criteria. So you have a yield, standard earth gravity, you have a force, and you have a fixed support at the bottom. Okay. So let me know your comments. I'll be there to help you. Thank you. Bye bye. Take care.